Theorem 2, criterion for an exact differential to exist, basically. Let's write this down. So let M and N be continuous and have continuous first partial derivatives in a rectangular region R defined by, so that's just some rectangular region, right? So that's the hypothesis of the theorem. Then this form is an exact differential if and only if the partial of m with respect to y equals the partial of n with respect to x. That may look familiar to you. That has to do with, in Calc 3, with conservative functions around a closed curve. With flux, you have flux going through something, and then you have this closed curve that is conserved, and you get zero. So that's kind of, it's all related somehow or another. Okay, but basically, if you can do that, you'll get that equal to zero, and it's part of that family of functions. So we're going to look at just one direction of this proof. It's pretty reasonable. The other one's a little longer. It's you can follow it, but it just take a lot of time. So take a look at that yourself. We're going basically, if this is true, then this has to be true. So if this is exact, this must be true. That's the direction we're going. This is a if P then Q. Take a look at your if and only if statements. So this is only if part. So this is P only if Q. If you say the other direction, then it's going if this, then this is exact. So anyway, here we go. So assume that that's exact. So your first statement, you got to assume the antecedent. So you assume P essentially. So assume M xy dx plus n xy dy is exact. Okay, so if it's exact, by definition, there exists, and sorry, handwriting's not very good tonight. There exists f and a function f such that for all x in the region R, m xy dx plus n xy dy is equal to partial f respect to x dx plus partial f respect to y dy. So therefore, m of xy is equal to that partial f respect to x, and n xy is equal to partial f respect to y. And what you do next is you differentiate again. And then, so now take the partial again of m, and we'll show it's equal to n. So we get partial m respect to y equal to partial respect to y of partial f respect to x. And that is just the second partial of f respect to y respect to x, which is equal to partial respect to x, partial f respect to y, which is partial n respect to y. Now, why are those equal? Why is this basically equal to this, even though you have x then y versus, or vice versa, I guess, y then x versus x then y? Because mixed partials are equal. Continuous mixed partials are equal. So that's true since and I'll say it like that since continuous mixed, sorry, my handwriting again tonight, continuous mixed partials are equal. Remember that in Calc 3. So you have mixed partial derivatives of any order, they are equal. Okay. So the other direction is on, you can take a look at that. They go through it maybe slightly differently in the book, but it's 60 through 61 or 60 and 61. And this is more for me and Nagel. And they describe this as more, the other direction is more of the procedure of how to find those partials, how to find f. So that's what they kind of reserve it for. So now let's move on to the examples. That's what we need to get to next. I'll show a few examples here before we go to the next section. So example 1, solve 2xy dx plus x squared minus 1 dy equal to 0. Now this one, there's different ways to solve these. I mean, basically, if you, let's see, if you just brought over, where is it? If you just brought over the function, you could, can you separate variables? Yeah, you probably could separate variables. You have to divide. It'd be a little weird. You have to divide out by one of those values, but you could. So you could you could just divide out by the x right there, and then bring it back over. But you could use separation of variables. But we're not, because we want to do it this way. So what we have, write down your m and your n. mxy is your 2xy, and n is your x squared minus 1. So now you want to check it. So this is what you will do to verify or check to make sure they're exact. You take those partials and see if they're equal. Since, that's period there. So since partial m respect to y is equal to 2x, which is equal to partial n with respect to x, then this given equation is exact. And you could say, by theorem 1 or something, but you don't have to say that kind of stuff. But you would have to show that step if it's asked to show something's exact. So therefore, if it is exact, there exists f of xy such that partial f respect to x equals the 2xy, and partial f with respect to y equals the x squared minus 1. So now you integrate either one of those. So this is a method that I like to use. This is really very similar to what we would have done in Calc 3 to find those functions. So I like to integrate both, and then you just compare it. They do show you a slightly different method, but let's just do that. Okay, so now integrate both. So you say f of xy is equal to the integral of partial f respect to x dx, which is equal to the integral of 2xy dx you integrate that and you get x squared y. And then what do you say after that? So it's usually what? Plus a constant. But if it's two variables, it could be any function of just y. So we say g of y. And integrate the other one, fxy equal to the integral partial f y dy, right, which is the integral of x squared minus 1 dy. Well, that one's easy. You just get y back in both of those, right? So you get, that's equal to x squared y minus y plus, and I'm going to say h of x. It's some function of just x. So now what I'd like to do next is just compare those. So then you write them down and you just say we have x squared y plus g of y is equal to x squared minus y plus h of x. So if that's the case, because they have to be the same, right? These functions, this is f of x. So what does it have to be the same? Well, my g of y has to be, so g of y has to be just the negative y. And then the h is gone. That's just going to be a constant. So therefore, my f of xy is equal to x squared y minus y. Well, that's it. And so now you can check. So I'll just say check it if you want. So you can easily check these by just doing those partials and just making sure you get the original function for the partial. So you do partial respect to x, partial respect to y, and see if you can put it in that form. So you should be able to check them pretty straightforward. And then you can actually solve this one. Oh, I almost forgot. That's not the solution. That's just f of xy. So the solution is f of xy equal to a constant, right? So it's got to be some constant. So if that's the case, then you would say x squared y minus y is equal to a constant. And then you can solve for y in this case if you want. So you can get an explicit solution for this one, like that. Factor out the y and divide, and there you go. So if it asks for explicit, then you want this form. If it just asks for a general solution, then you can write the other form. That's fine. So either one of those will work. So one is general. Okay, so this is general. This is explicit. Okay. Also just note here, in this form, you can't have x be plus or minus 1. So you lose those solutions in that explicit form than you do in the implicit form. Haven't talked a whole lot about that, but just keep in mind that denominator sometimes. Okay, so the next ones, I'll put them up there, and you can write them down. I won't go through all the details. Okay, so we're going back to this question. This is example 2. The next example. Okay, I don't think it'll fit right there. Let's check it out. Maybe it will. Yeah, it does. Okay, so here's example 2. Let's go through it a little bit. So solve this, and it usually tells you in this case it's exact. So in some cases I'll have to say what it is. In some cases I'll just say solve. So here's your mx, here's your ny. You do the partials, make sure they're equal, therefore exact. Then you have the existence of your function f. So here's your two functions. Then this is the technique I like to do. I'm going to integrate both of them, and you get this, and then you just compare. You compare what it must be, what your g of y must be, and your h of x must be. Once you compare it, then you just line them up. Okay, and then but you got to put it in this form. So this form set equal to 0, and you could, it doesn't matter whether it's set equal to 0 or set equal to the constant. That's just the form. So that's the family of solutions when you say f of xy equals 0. Or you can, if you want, you can just say x e to the 2y minus sine xy plus y squared equal to a constant. Because it is arbitrary. So that's what they call the family of solutions of the exact equation. Okay, and I'll show you one more. This is an initial value question. Okay, so here's example 3. Should pretty much, there's one more thing about in that section. They do one example in there that is about what do they call it? The substituting mu on both sides to make the form exact, and an integrating factor again concept. We'll get to that in the next section. Okay, so here's the next question. This is then put in this form. Okay, so you have to expand it out so you can write m and n, and then show that they're the same by doing their partials, therefore exact. Then there must be the existence of f of xy. Okay, so now you integrate both sides. Oh, and then when I did this integration, when you do this integration, you either have to pick u to be sine or u to be cosine. It doesn't matter which direction you go. Okay, so you could end up with a solution that has cosine squared down here, but it would basically ends up changing that constant. Okay, so go through the rest of that, try it on your own, and see if you get the same thing. Okay, then you can jump into the problems from the book.